Ever wonder how scientists predict the shaking from a massive earthquake? It's not just guesswork.
No, it's a fascinating blend of observation and simulation.
This paper dives into simulating the 2022 Luding earthquake in China. Pretty intense stuff.
Yeah, it was a powerful quake, and this study uses some clever techniques to model its effects.
So they're basically trying to recreate the earthquake's ground motion using computer models, right?
Right.
They use something called Stochastic Finite-Fault modeling, or SFFM. What's the gist of that?
It breaks down the earthquake's fault into smaller pieces and simulates each one's contribution to the shaking. Then it adds them all up.
Like a puzzle, but with seismic waves. That's cool.
Exactly. It considers the source, the path the waves travel, and how the ground amplifies the shaking.
So they needed a lot of input data for this model, right?
Absolutely. Things like the earthquake's magnitude, fault geometry, and the properties of the Earth's crust along the wave path.
And what about the ground itself? How does that factor in?
That's the site amplification. Different types of soil and rock amplify the shaking differently. They used a classification system to account for this.
So sandy soil might shake more than solid rock?
Generally, yes. The model accounts for that variation.
Did the model perfectly match the real-world observations?
Not perfectly, no. It did a great job for many stations, but there were some discrepancies.
Oh, really? What caused those differences?
Near-field stations showed higher simulated shaking at high frequencies than observed. This is likely due to nonlinear soil behavior.
I see. And what about the far-field stations?
Far-field stations showed lower simulated high-frequency shaking. This was likely due to the complex geology of the long-mentioned fault zone.
So the soil near the epicenter acted differently than expected under strong shaking?
Yes, the nonlinearity reduced the high-frequency amplification. Think of it like a sponge. It compresses under pressure.
Right. So the model didn't account for that compression effect?
Not fully. It's a complex phenomenon.
And the far-field discrepancies were due to the fault zone's complex structure?
Yes, the crustal heterogeneity affected wave attenuation. They used a quality factor, Q, to represent this.
So Q represents how much as the seismic waves lose energy as they travel.
Precisely. The initial Q value didn't capture the heterogeneity of the fault zone.
So they recalculated Q using data from the fault zone?
Yes, and that improved the model's accuracy for the far-field stations.
So what are the key takeaways for improving these simulations?
Accounting for nonlinear side effects and using a more realistic Q value that reflects the crustal heterogeneity are crucial.
Makes sense. Essentially making the model more realistic by incorporating the complexities of the real world.
Exactly. It highlights the importance of detailed geological information.
So this research shows that while SFFM is a powerful tool, it needs refinements to accurately capture the complexities of real earthquakes.
Absolutely. The study highlights the need for more detailed site characterization and accounting for the complex geological settings.
It's a reminder that even the best models are only as good as the data they're based on. What kind of future research could build on this work?
More detailed studies of nonlinear side effects and improved methods for characterizing crustal heterogeneity are needed.
And that would lead to more accurate earthquake simulations, which could help with disaster preparedness. So how can this research help in the real world?
More accurate simulations can improve building codes and emergency response planning.
Better predictions mean better safety measures. That's important. Were there any limitations to this study?
The limited strong motion data for some stations affected the analysis of nonlinear side effects.
So more data would improve the model's accuracy even further. This research is really important because it helps us understand the limitations of current earthquake simulation techniques.
And it points the way towards more accurate and reliable models for future earthquake hazard assessments. It's a great example of how scientific modeling constantly evolves as we learn more about the complexities of the natural world.
That was a great discussion. Thanks for sharing your expertise.